In my last video, I described the data warehouse workload and some high-level concepts around architecting the proper hardware solution for a data warehouse workload. If you have not done so, please go back and watch that, as it forms the foundation for this and subsequent presentations. So once you have been able to measure the hardware capabilities of your data warehouse server by using SQL IO, then the next step is to measure the size of your queries, and then either architect or buy through the Fast Track appliances the correct hardware solution that you need. So I will describe in subsequent videos SQL IO more in detail, but now I'm going to start with measuring your query size. So this is a very simple and straightforward type of exercise, but without knowing this, it is impossible to pick or architect the correct hardware solution. So the basic formula is at the top. Your query size, in other words, the amount of data returned by your query, divided by the megabits per second of your hardware solution, gives you a certain response time. So each one of these three components can be substituted for and solved for to find the optimal solution for your data warehouse. And I've listed two examples below that. So for example, a 50 gigabit query, so this is a query that returns 50 gigabytes of data, assuming that the hardware is able to deliver 1.5 gigabytes per second, yields a minimum query response time of 33 seconds. In other words, it's just very simple math here. So if you want a query response time of 33 seconds and you know your query sizes are about 50 gigabytes, then you need at least 1.5 gigabytes of throughput to be able to deliver that query within the desired time frame. So this then provides a framework for understanding what kind of performance you should expect from your data warehouse that you currently have, or if you're trying to build a new one, how much throughput it needs to have this desired response time. And so, and continuing on with this example, if for some reason 30 seconds is not fast enough and the business desires more performance, let's say they want to cut that response time in half to about 15 seconds, then all you need to do is double the throughput. So instead of being 1.5 gigabytes per second, then it needs to be 3 gigabytes per second. So same 50 gigabit query divided by 3 gigabytes per second yields a minimum query response time of 16 seconds. So the minimum response time is 16 seconds for this particular query. Again, this minimum response time is not a database engine limitation, but a physical limitation on the hardware. No database engine will be able to perform faster than the hardware is capable of performing at. So this will let you appropriately set expectations with the business, saying, okay business, this is how big your queries are. If you want them to come back in 30 seconds or 15 seconds, these are the types of investments we have to make on the hardware side. And of course, the larger the throughput, the bigger the hardware investment will have to be, but it should yield better performance. And this way you can set parameters around that discussion instead of just guessing and hoping for the best. A note here, so I have a big star here. These minimum query response times do not factor in CPU cycles. So this is just the minimum time required to move the data from storage to the SQL server, to the database engine. Now, how long it takes to process depends on how complex that query logic is, that aggregation logic. Very complex logic can take a lot more CPU cycles than very simple logic. And I'll address those kind of things a little bit later. But this is the core and the foundation and the beginning point of being able to start thinking about data warehouse performance. So now I'm going to continue with a series of demos. I'm going to use several commands. I'm going to use SQL Server and several techniques around that to demonstrate query IO statistics, the advantages of using things like page compression and new Columnstore indexes new to SQL Server 2012. Later on, I'll also get into an extended events framework that makes capturing all the data that I described previously much easier, much more straightforward and manageable. So now here I have in Management Studio, I have a test database. And in this test database, I'm going to begin with a table by creating a table called no compression underscore 10m, meaning this is there's no compression on this table. It is a 10 million row table. I created this table simply by using a Cartesian join of an AdventureWorks Internet Fact sales table. I'm not going to demonstrate creating this table because it takes on my laptop several minutes to create, but I already went ahead and created it ahead of time using that. And all these scripts will be available as links at the bottom of this video and also on my blog. So once the table was created, I created two, one without compression and one with compression. So the page compression 10 million row fact table has identical data. They have identical data in them. Only the difference is one of them has data compression turned on, and that's the one labeled page compression underscore 10m, 10 million rows. So, and I'll come back to that in a little bit. But what I'm going to start with here is the non-compressed table. So this is a 10 million row fact table, has no compression, and has no indexes, and I'll get to why I did that to begin with. And I'm going to select from it. I'm going to select from it using a very simple query. It's just going to select the sales territory and aggregate by sales amount, and I have a group by on here. Now this is, for demonstration purposes, a very simple query, but it still accurately represents a typical data warehouse query load. So with this simple query, I'm also going to drop my buffers. This is very important because this cleans out memory. That means I'm not getting any data from memory or from my caches on the SQL Server side. That all these requests are going to have to be satisfied from storage, from my disk where the data is stored. I do this to simulate data warehouse workloads because most data warehouse queries are too large to fit in memory by definition. And so here I'm simulating that scenario. In real life, in production, you might have some of the data reside in cache or memory, but still a majority of it will be coming from disk. The second line, line 29, I'm setting IO statistics on, and this will allow me to measure the size of the query. I also set time on just as something to consider in terms of CPU cycles. So if I execute this, now this is going to take about 13 seconds to execute. And while it's executing, I want to explain, because I have no indexes on this, that this query, instead of returning just 2 columns worth of data from the underlying fact table, is going to return all the data from the fact table. That's because data is stored in a row format, and requests are satisfied row by row. Okay, so now the query has come back, and because I turned on my IO statistics and my time statistics, I have an additional tab, Messages, that gives me the statistics for this particular query. I'm going to scroll down to the bottom. Now the important thing to look at here is, here's my table that I was querying, my fact table. And I have a scan count, a logical reads, physical reads and read aheads. Now, in case you didn't know, so because I dropped all my buffers, my caches, my memory caches for SQL Server, all the data had to come from disk. Now, under normal situations, a database engine, when it requests data, will request data page by page. So we're talking about a database file page, which represents 8 bytes. But SQL Server has the ability in what's called a read-ahead scenario to recognize, hey, you might not want 1 page per I/O in an out request. You may want several pages, and in fact, in most data warehouse queries, almost all of them, you will want many pages of data to be read. Remember that historical data. So instead of satisfying that I/O request with what it requested with 1 page, SQL Server goes ahead and scans in many pages and sends that from storage to the server. So in this case, it's 208,000 pages were scanned using read-ahead. And that's why my physical reads are so low, in this case 0. My logical reads, so once data is scanned from the storage, it goes into SQL Server memory temporarily before it goes onto the CPU to be aggregated. So my true count of pages can be different depending on the read-aheads and then on the logical reads. So the best measure of how big this query is should be, you should use your logical reads. Again, in this case, this matches perfectly, but in normal situations, you might have some of this data reside both in memory and on disk. But logical reads will always be the combination of both. So that's the one you should use. And then so you take logical reads, and because there are 8 bytes per page, you times by 8 divided by 1024 will convert that into megabytes. So in this case, this query is 1600 megabytes in size, which, because I have no indexes created on this table, means that the entire table's data was queried. Not just the data for individual columns, but data for the entire rows, for all rows of this table. This is very important because under normal situations, data is stored in a row-wise format. We can verify this if I go to my no compression table and I click properties. Lo and behold, the data space for this table matches exactly with the query size, which makes sense because my query returned all the data from the table, 1600 megabytes. So that way I know my calculation is correct. So that is a very basic query against the table, and the point of this is to illustrate that even though this query requested 2 columns, in fact all columns are returned in the query from storage. This would be an inefficient process if this was the only query process available for data warehouse type workloads. So starting in SQL Server 2008, there was the ability to compress a table's data. So it's still stored in a row-wise format, but this time it is compressed. And what that means is a database page, and I'll get more in details later on, but a database page has really kind of 2 parts to it. It has a header, which is kind of metadata information, and then it has the body, which holds the actual rows of data. And so what compression does is store in the header metadata about the unique values in the body. So that way the body data can be compressed and only store unique values. Any repeating values in the rows can be stored as single distinct values. And that has the effect of being able to store more data in a fewer number of pages. And if there's fewer number of pages that represent that table data, then a fewer number of pages need to be queried. So as before, I'm going to query the table This time it's the page compression table because this is the one with page compression turned on. And I'm going to use the same thing that I used before and drop my buffers, my caches, and I'm going to turn on IO statistics so I can measure how big this query is. So if I run that, recall that the previous query took about 13 seconds to run. Well, this one only takes slightly over a second to run. Why the dramatic difference? Well, the dramatic difference is because of this page compression. So, and if I flip over to my messages and copy and paste this, like I have above in green, what you see is that my logical reads, instead of being about 208,000 from before, now are simply 21,000. So there was a lot fewer read-aheads or logical reads for this particular query, meaning fewer pages will have to be had to be returned from storage because of that compression. And the math is pretty straightforward. Again, I take my logical reads times 8 divided by 1024 gives me 167 megabytes returned by this query. This query queries the entire table's worth of data. Whereas previously, so as you can see from the calculation here, the compressed form of this exact same table is actually on the order of the 10th of the size of the original table, and so therefore requires less throughput capabilities. In other words, it makes more efficient use of the throughput capabilities of SQL Server. Now, a word of caution here. Page compression comes at a price, and usually this is a good trade-off in a typical data warehouse scenario, and the price is processor. So what I have up on the screen is the message from my non-compressed table, 208,000 logical reads. And as you can see, the CPU time is 5,400 milliseconds. However, this query takes about 13 to 14 seconds to complete on my laptop. Now, if you compare that, remember that 5,400 milliseconds. Although the total query time is a lot larger because it's just waiting for data to travel from my storage to my CPU, the CPU time is 5,400 milliseconds. Now if I run the same exact query on the page compressed table, my total elapsed time for the query is about a second, a little over a second. However, my CPU time has now increased from 5,400 milliseconds to 7,800 milliseconds. So in other words, when data is inputted or written, it needs to be first compressed on the CPU, then moved to storage and stored there. And so when data is queried, it is queried in a compressed format. It goes into memory. It even resides in memory in the compressed format, and then only when it's processed on the CPU are there more CPU cycles spent to decompress that data and perform whatever, in this case, aggregation logic is required of the CPU. So you're going to pay a price on your CPU. More CPU cycles burnt to perform the logical operations of decompression and compression and decompression. But that comes at in this case, a tenth or a tenth of a savings, or 10 times savings in the throughput of this SQL Server. That's why my query is able to be completed in such a timely manner. And what I've seen from my experience is usually the CPU hit is on the order of 3 to 5% increase in CPU. Now this will vary dramatically on the data types you use. So using things like integers becomes very important. If you use lots of characters, strings, and things like that, your CPU time is going to dramatically increase. And this is only for data warehouse workloads. You can, and you might experience some benefit to using it in OLTP type environments, but that needs to be thoroughly tested because it's not always going to be a good trade-off in OLTP type workloads. But for data warehouse workloads, it's almost always a good trade-off if you don't have column store indexes. So new to SQL Server 2012 and also greatly improved in SQL Server 2014 are column store indexes. So now for my column store index. Now, before I continue on with the column store index, I want to point out real quickly for the page compressed table, because this query, to verify this, that it in fact does query the entire table, 167 megabytes, I can go to my properties of the table, pull up the storage size, and in fact that's exactly the same thing, 167 megabytes. So in other words, not only are queries faster, but my storage is much more efficient. Now this, both the performance and the storage of this will highly depend on, one, your data model, conforming to dimensional modeling, fact table, particularly having all integers in that fact table, and also the cardinality of your data. Remember, it's trying to fit as many rows as it can, distinct values within those rows, onto a single page. So if you have lots of unique values, low cardinality, then that will not compress as well as many repeating values, high cardinality. So that your data, again, your data modeling and even the nature of the data itself will determine how much benefit you get from this page compression. And the same principle holds true for when I switch over to column stores. So I will have an entire series of videos dedicated to column store indexes, but I wanted to introduce this real quickly just to give you some background here and an understanding before I dive deeper. So here's my query. Now my column store query, I actually made a column store index fact table. Instead of being 10 million rows, I used the exact same query, but I have it now as at 100 million rows, because the 10 million row fact table didn't really show off the performance difference too much for column store indexes. And real quickly, so here's my column store index 100 million row fact table. As you can see, it's an exact replica of the other one, and there's only one column store index. And for this column store index, the best practice is to go ahead and include all the columns into a single column store index, and that's really all you need to do for a column store index for your fact table. Now, I have this option to query this table without a column store index, and I went ahead and did that ahead of time. Now remember, this has 10 times the data of my 10 million row fact table. So it stands to reason, and it does turn out that it roughly has to do 10 times the number of logical reads. So previously, for my non-compressed fact table, it was 208,000 reads. This one is 2 million reads, right? So about 10 times more, which is to be expected. And the total elapsed time, instead of being about 13 or 14 seconds, now jumps all the way up to somewhere on the order of 14 minutes, 14 to 15 minutes. And in fact, the entire table's data is returned, and the entire table, the size of the table is almost exactly 10 times larger than the 10 million row fact table. So however, with SQL Server 2012, you can create a column store index, and a column store index is similar to another index in any other index in that the index is a separate representation from the table's data. So you have the table data in a row-wise format, and that's still there. The table still exists. However, in the non-clustered column store index, you have a separate representation of that table's data in that index, just like similar to how the other indexes work as well. Indexes are simply different separate representations of the underlying fact table data. So, and if I run this same command against 10 times the data with a column store index on it, this time I'm choosing to ignore that, and I execute this query, it comes back in less than a second, even though it is literally querying 10 times the amount of data. And I'll get into more as to how Columnstore technology accomplishes this, but if you go to the messages for this, what you can see, the reason why this query performs so well is similar to the way in which page compression, why page compression performs so well. It's because I greatly reduced the number of my logical reads. From originally without Columnstore Index 2 million logical reads to just over 1,000. And in fact, if you do the math on this, this means that the column store representation of this particular table is about a megabyte in size. And that means a roughly 2 gigabytes of data is represented by the column store index in 1 megabyte. And so at most, only 1 megabyte needs to travel from storage to your processor to be processed. And this can amount, as you can now understand, to a tremendous performance increase, a better utilization of that data warehouse server's throughput, because no longer will 2 gigabytes be traveling over those I/O component interfaces. Now only a megabyte will be traveling over those I/O component interfaces. So real quickly, just to wrap up, if you go back here, now I've walked you through several scenarios, and I'm going to explain several others as well, particularly going more in detail with indexing. But now you can see how you can start planning out. First, you need to be able to measure the size of your queries, compare that to the throughput capabilities of your server, whether currently or whatever you want to buy, to get a desired query response time. And again, remember, these calculations do not take CPU time or CPU cycles into effect. That has to be calculated as well later on. So I will also in future videos introduce the concept of extended events. They are a great enhancement to capturing all these I/O statistics or any other types of statistics that you want. They're also new in SQL Server 2012, but they capture these I/O statistics. Instead of doing it on a one-by-one basis with each query, you can just turn on your extended event, and it will capture all these I/O statistics for you. And I have sample queries that will handle all that for you as well, that I use. So thank you for watching.